Thank you.
Okay, well, thank you very much for inviting me. So I am from Birkbeck, which is a slightly unusual part of the University of London because we teach in the evening and we mostly teach part-time students. I'm also at the moment from Jacobs because I'm on a 3-year fellowship supported by the Royal Society to support collaborations between universities and industry. So this work actually predates that, but I just thought I'd put everybody's logos on anyway. And I also need to name check my co-authors who aren't here. So Martin Bates is the driving force of most of this work. He's been working in Sussex for about 40 years. And Jenny did all the uplift modelling because she's much more numerate than I am. Jean-Luc did the OSL, and we also had some fossil work, which John Whitaker did, who's sadly no longer with us. And we recently published this last year, and it's open access. So if you want to read more, that is the link, and that'll be available in the slides when they are put up online later. Okay, so I'm going to start by giving a bit of a context and what the aims of this study was, and then introduce you to the glorious Sussex coastal plain, my own motherland, although actually I came from a little bit further east. And then talk about this new way of how you estimate past sea levels, this indicative meaning, which is a bit obscure, how we applied it to the Sussex coastal plain, how we did the uplift modelling, and what we concluded about the landscape as a result. And then there's a list of resources as well. Oh, no. Okay, so past global sea levels are really important for future sea level estimates. So there's a lot of work that uses the last interglacial, so 125,000 years ago, as a picture of what might happen in the future with higher sea levels. But they're built on these local estimates. So the local estimates are relative sea level only. So it's not a measure of global sea level. So there's a lot of uncertainty going between the local estimates and the global estimate. So you need to try and minimize the amount of uncertainty in the local estimates. And that's kind of what we're doing. So the way to do that is to understand what these little fragments of evidence for past sea levels in different landscapes really mean, which nobody has time to do when they're doing the big compilations. So lots of global reconstructions have used data from the Sussex coastal plain, but they haven't completely understood the sequences because they've just applied a general model to it. So our aims were to recalculate relative sea level values based on the fact that there are sequences and we know them, and then to model uplift rates using a new technique that so Jenny works in the same university as me, slightly different department, but we're in the same building. And they were applying this uplift modelling to fault movements in Greece and Italy. And I thought to myself, hang on, we can do that. So we brought Jenny on board to apply it to this slightly different setting. Well, very different setting because we don't get earthquakes. Okay, so just start off with a bit of an introduction to the Sussex coastal plain so that our data makes sense when I get to it. So this is the unbelievably complicated structural setting. So I'm not a structural geologist, so I'm not going to tell you about it in detail. But broadly, the Sussex coastal plain is within that red box, or the western part of it is Hampshire, but it's the same geomorphological feature. It's kind of on the edge of the Hampshire Basin. It's bounded to the north by a couple of anticlines and then a syncline. And then to the south, you've got the unbelievable complexity that is the Isle of Wight. And this is what it looks like topographically. So you can see the South Downs. There we go. The South Downs coming along from Winchester all the way through here towards Brighton, and then another area of high ground in the Isle of Wight. Oh, there we go, there's my cursor. And then in between, it's much more low-lying. And the other thing you can see is that there are a series of rivers that cut across. And so you've got, and they're all tributaries of the River Test, which forms Southampton Water. So you've got two structures with the rivers cutting through. At the present day, you have very few cliffs. So you have some cliffs on the Isle of Wight over here on the west, these little hatched signs, and then cliffs over here near Eastbourne and Seaford. And then in between, the type of coastal environments we have are much more low-lying. And you can see that just shows you where the longshore transport goes. Okay, so the geology, because of this anticline syncline system where they're quite close together, what you've got is two lots of chalk, which becomes important when we start thinking about the sea level history later. So you've got the main chalk of the South Downs here to the north of Brighton, and then you've got Lambeth and Thames Group here, and then another two little outliers of chalk, but they don't join up, and then you're back onto the less competent rocks. So it's a very complicated landscape to then superimpose changing sea levels onto, which means that we end up with a very fragmented record of different sea level events, different high sea level events. Okay, and then when you put quaternary sediments on top of that, you can see that over in the west, all those yellow blobs are river gravels. They're gravels of the former river Solent, which no longer exists because various barriers got breached. And then over in the east, you've got these different raised beach deposits, basically. So the green is the Goodwood's Linden Formation. The purple is the Aldingbourne Formation. It's not nearly as well defined as it looks on the map. This light green is the Brighton Norton raised beach, and I'm going to show you pictures of all of these because it's the end of the working day and we need pictures. And then in the really low-lying area where there's no chalk underneath at all, you've got the Pagham Formation, which we'll find out later. So most of the work we did was on this bit here between Chichester and Brighton, but we have also looked at an estuarine sequence at Stone Point, at Leap Country Park, and another sequence at Bembridge on the eastern edge of the Isle of Wight. And Bembridge becomes really important because, well, you'll see later. Okay, so what are the raised beach sequences? They're not just those little blobs on the map. So the Goodwood's Linden Formation, the dark green in the nasty blow up on the right there. The most famous site in the Goodwood's Linden Formation is at Boxgrove. So this was a quarry where they found a lot of archaeology and had to stop. So broadly, there's a wave cut platform at the bottom. I'm sorry about the state of this picture. It was the best one I could find. So wave cut platform at the bottom, covered with a few cycles of marine silts, and then slope deposits. And there's archaeology in both parts of the sequence, so the marine silts and the slope deposits. And in the marine silts, it's very well preserved. So there's one location where there's a kind of triangular flint scatter, and you can see where the person was sitting in order to make their stone tools, because there's just this pile of flint debris in between their legs. They were kind of sitting with their legs in a triangle shape. So lots and lots of hand axes, which archaeologists get excited about. But more exciting, a human tibia and 2 human incisors. So this wouldn't be anatomically modern humans. This would be an earlier hominin. But you just don't find remains of hominins at all. They just don't preserve. As like the apex predator, there's just not very much of them. And so the chances of them preserving are quite low. So Boxgrove is a really important site, giving us a little window into what life was like during the high sea level that was the Goodwood-Linden Formation. And the biostratigraphy suggests that this happened just before the largest ice expansion in the UK, so around about 500,000 years ago. And so the diagram on the bottom just gives you a picture of how these raised beaches kind of go down the hill from the Goodwood-Linden at the very top to the coast. And you can see the orange, which is the covering of slope deposits, and there's a lot of that. But it's possible to reconstruct where the coastline was. So the silts suggest that it was pretty low energy environment. So it must have been a closed embayment. And of course, we've got these 2 chalk outliers, which would create that closed embayment if they hadn't been eroded away, which we think they weren't at that stage. So you've got, this is where the Goodwood-Linden beach is, and you've got the coastline in this embayment, and then coming out on either side. So I should have said, if at any point I'm not clear, just stop and ask me a question as we go along, because no point getting lost, particularly when there's so few of us. Okay, so I've skipped over the Aldingbourne beach, which is the purple one, because calling it a raised beach is a bit optimistic. It's basically a series of patches of gravel that have no relationship to a cliff line, and we have no idea how old they are, and most of the fossils have dissolved. So it's kind of a raised beach, but it's kind of also a bit of an enigma. So we are skipping on to the light green, which is the Brighton Norton Formation, which is the next one that has a proper cliff line. And the best place to see the cliff line in the Brighton Norton Formation is behind Asda at Brighton Marina. It's very salubrious, but it's quite handy for taking students too. So you can see up here in the top left, this is it's called Black Rock for some reason, but it's basically Brighton Marina. So you've got the chalk in situ here, and this is where the cliff line was, where I've put the red line. And then you've got a big cliff fall of really fresh chalk and flints. And then as you go west, it becomes more like a normal beach, and you can see a close-up of it in the bottom there. And then that is covered in significant thickness of slope deposits. So that's the best exposure, but it doesn't have anything suitable to find out how old it is. So back in the late 90s, Martin dug a great big hole at Norton Farm. In fact, 2 great big holes, one up here in the Aldingbourne raised beach and one down here in the Brighton Norton raised beach. And he luminescence dated them, and these dates are about 240,000 years ago. So younger than Boxgrove, but older than the last sea level high stand at 125,000 years ago. And the paleogeography at this time was a bit different, which you can tell from the fact that it's a bit more continuous. So we seem to have eroded those 2 chalk outliers, and the coastline is in front of that. Okay, so that's the Brighton Norton Formation, this one here. The interesting thing about this is it's on the transition between 2 different rock types as well. So it makes the preservation of the cliff line a bit odd. Okay, so then if we go down into the bottom of the sequence, you can see that there's some silts, some gravels, some rounded gravels, some sands. Won't talk about the channels underneath because that's just an extra level of complexity. But it's mostly, this Pagham Formation stuff is mostly sitting on Lambeth Group and Thames Group, with a little bit of Bracklesham beds at the southern tip of Selsey Bill. Okay, so these are the last interglacial sequences. We've also got last interglacial sequences, remember I was saying, to the west, on the mainland and also on the Isle of Wight. So at a place called Stone Point or Leap, we've got about 8 meters of salt marsh sediments, which we cored. And then on the Isle of Wight, there's quite a complicated sequence at Bembridge, which sadly I don't have any photos of, so I'm going to tell you about now before I show you the pictures of Leap. So there is actually a cliff line, and there's a very thick beach, and then a little way over there's a thin salt marsh deposit. So it's a really complicated coastal deposit, but it's been luminescence dated to 125,000 years ago, so it's definitely from the last sea level high stand. And then on the Sussex coastal plain, what you have is a series of really unsatisfactory bits of sand that don't really relate to each other or to a fossil cliff line at all. So the only fossil cliff line is, oh, I'm going all over the place, there we go, is at the Isle of Wight at Bembridge. And multiple sites have OSL ages, as you can see from the teeny weeny print next to the boreholes. So this is not a great picture of the Stone Point estuarine deposits because they get a lot thicker and they've got peat beds in them. But this is at the most landward extent where it sits on top of river gravels. And then this is just a couple of pictures of what the Pagham Formation looks like. So the best version of it is in a very low cliff at Selsey on the left there, which we OSL dated. And then the picture on the right from Pagham Water Treatment Works is much more common. So there's some brick earth on the top, and then there's marine sands. So, and these marine sands are varying thicknesses, but mostly not very thick. And they sometimes have fossils in them and sometimes don't. But quite a lot of them are OSL dated. And that was Martin doing a lot of commercial geoarchaeology over an extended period, and always getting them to OSL date the test pits. So he built that up over a long time. Yeah, so once we're into the Pagham Formation, you can see that the coastline is, as you might expect, closer to that of the present day. And you've got these kind of ridge formations, but no obvious cliff line. And that's why the coast is dotted, because we don't really know where the northern edge of the coast was. And you can see that there's Leap and Bembridge over on the western edge as well. Okay, so now it gets a bit technical, so do stop me and ask questions if I go too technical. Just going to try and talk you through how you estimate past sea levels using this indicative meaning approach. So we've already said that past global sea levels are really important for future sea level estimates. And these days we can measure it using satellites, and that's great because we only have to correct for ocean currents and the curvature of the Earth. But before the satellite era, so before around 1979, all of the records are from tide gauges, and then before that from sediments. So that's obviously relative sea levels, they're local estimates, and they're not the same as global sea level because the land is able to move as well as the sea. So in order to use these relative sea levels to estimate global sea levels, we need to allow for land movements over time, which our study wasn't about. And we need to have a proper understanding of how the evidence of past sea levels actually relate to mean sea level. So we need to understand the geomorphology at the present day. We need to use modern analogues, basically. So if we have a wave cut platform in chalk, we can go and have a look at where the wave cut platform forms in relation to mean sea level and at the present day. And that matters because obviously the tidal range in the UK is quite large. So where Jenny was working in Greece and Italy, their tidal range is about 50 centimetres. And so if you've got a wave cut platform, that is mean sea level. But our tidal range is more like 5 or 6 metres. So we have to think a bit harder about how mean sea level relates to the feature that we see in the landscape. So I'm starting off more easily with sea level index points. So don't know if you've ever been on one of those field trips where they make you identify salt marsh plants. Maybe it was just me. People lost their wellies. They made you do it in October. It was usually raining. But you can tell how high in the marsh you are based on the vegetation. They have really distinct elevation ranges for plants, but also for rams and ostracods and diatoms. And obviously that's because of the amount of inundation that they receive and how much salt they can cope with. So they can create these things called sea level index points with quite a lot of precision because they know they've got this particular group of fauna or flora, and that must be like a 50 centimetre or a metre window of relationship to mean sea level. That really only works for the Holocene. When you get further back in time, the fauna are much harder to interpret. But you can nonetheless say, well, there's some marine stuff in here, so it must have been at least this elevation. So you call that marine limiting, or if there's no marine fossils, then you call it terrestrial limiting. So this worked really well looking at sea level in the Holocene. But when people started wanting to go further back in time, they realized that it didn't apply to geomorphology. And the geomorphology is what we're using to estimate these former high sea level events that are earlier than the Holocene. So they came up with this unbelievably complicated process. And it's even more complicated if you have a more complicated geomorphological feature. So they've got a diagram that looks a bit like this for all of those sea level indicators that are listed on the right-hand side of the slide. So basically what they've done is they have come up with some terminology for a key tie point on the geomorphological feature and how it relates to mean sea level. So in this case, we've got the inner margin of a marine terrace. So we have, so this is the former marine terrace, and that's like the inner margin. So that's never as definitive as that in the real data, but that's how they've drawn it. And so they've got an elevation of the sea level indicator, which comes across here in the red. But was that relative sea level? Well, it depends. So then you look at your modern analogue, which is down here at the bottom, and you can see that mean sea level is up here, which is considerably higher than the equivalent feature in the modern analogue. Does that kind of make sense? Okay, cool. And then you've got all these like equations that you don't need to worry about. But broadly, it's about what is the relationship between mean sea level and that feature in your modern analogue. So you need to choose the right modern analogue, and then you need to get the data to make those measurements. And you can see here that if you were estimating relative sea level just based on the elevation, it would be at 2 meters. And if you do the correction for where it is in relation to mean sea level in the modern analogue, then relative sea level is a bit higher, between 3 and 4 meters. So our job was to go out and find the modern analogues for key locations and to apply this methodology, which actually, once you've got it into a spreadsheet, isn't quite as bad as it looks in this diagram. Okay, so the reason we did it on the Sussex coastal plain is because they actually have a really complete record of former sea levels. Lots of places you only have like one raised beach from one former high stand. So it's a good place to do it. Not all of them have these wave cut platforms. So what we decided was we would estimate indicative meanings for all of the sequences, but we wouldn't necessarily use them all for uplift modeling because, well, you'll see why in a minute. And as I said before, there's various large-scale reconstructions that have estimated past sea levels from this region based on generalized relationships with mean sea level, but we were using modern analog data. So what can we use in Sussex? So like I'm saying, the marine terraces are the best, and they have a really close relationship to the high stand, and they're a really clear geomorphological feature. And we find those at Boxgrove, Norton Farm, and Bembridge. Obviously, there's also a marine terrace at Blackrock in Brighton, but we don't have any age estimates from that, so we're not able to use that. We have beach deposits, so they have a much looser relationship to the high stand because they haven't got the edge of the wave cut platform. So that's the Aldingbourne Formation and the Pagham Formation. And then you've got these salt marsh estuary deposits. So other people were a bit more optimistic about their ability to use them as sea level index points. I was not convinced personally, so we didn't do that. Okay, so for Boxgrove and Norton Farm, they're both cliff lines in chalk. So I went to Seaford Head as being the nearest chalk cliff. So there's a lovely picture of lovely Seaford Head. And then what we did was we got, so the Channel Coast Observatory have cross sections across bits of coast. So I chose a couple of lines going across Seaford Head and plotted those out and tried to estimate where the break on the edge of the cliff was in relation to mean sea level, and then applied that to both Boxgrove. So this is the Boxgrove sequence, and this is the Norton Farm sequence. And you can see that actually trying to work out where the inner edge of the marine terrace in both of those is quite difficult because it's quite sloped. So we just came up with some kind of approximation based on what looked plausible and then gave it an error margin. So that was how we corrected those ones. And can I see what the difference is? So the lines that go across are the actual measured elevation, and then these crosses here are the corrected elevations. So they're just slightly lower. At Bembridge, this is in, it's not called the Bembridge Miles anymore, but I can't remember what it is called. But it's softer. So you can see that this modern analogue at Hampstead Cliffs is much less clear where the edge of the cliff is and where the beginning of the wave cut platform is. But nonetheless, we did the same thing there. And we came up with some approximation of where the bottom of the cliff was and corrected those elevation estimates as well. And again, the paleo cliff line is not very clear either, but we did our best. And then we took all the different beach deposits from the Pagham Formation. We didn't worry about the Aldingbourne. And we took Selsey West Beach as a modern analogue. So that's on the edge of Selsey Bill, just south of Chichester, and just along the coast from the unbelievably fancy beach resort at West Wittering, where it costs you literally 15 quid to park in a field next to the coast. And we used the beach deposits to estimate relative sea level. So the actual elevations are on the left, and the new estimated relative sea levels on the right. And you can see two things. One is that they are marginally lower. And two is that the error margin gets larger, because you can see that we have no idea which part of the storm beach the little scrappy bits of sand that Martin found in test pits actually relate to. So we had to give it a really big error margin when mapping those beach deposits onto the modern analogue. And so those error margins are so large as to be practically unusable. So you've got like 10 meters from one end to the other. So we did that, but mostly just to show that you can't really use those deposits to do what people have tried to do in the past. Okay, so moving on to the modelling. So uplift rates are likely to be very low, but there are some compressive stresses because you're on a passive margin. And then, of course, you've got an interaction with the land going up and down as it gets loaded with ice sheets at varying distances over multiple cycles. So people have calculated uplift rates in this region before, but they haven't done the indicative meaning thing. And the other thing they've done is they've ignored the fact that different sea level high stands are actually at different elevations. So the last interglacial at 125,000 year, that high stand is significantly higher than the one at 200,000 years ago and also the one at 240,000 years ago. So if you've got low uplift and you've got a high sea level event coming after a lower high sea level event, if that makes sense, then the danger is that you overprint and you lose a sequence. So people were kind of counting back and going, well, that one's the last interglacial, so the next one up must be the next, and so on and so forth. But actually you could lose entire high stands because the uplift rate is so low. So what Jenny did was she applied this thing called synchronous correlation, which accounts for different high stand elevations. It basically takes a couple of tie points in the sequence and then projects where the different sizes of high stands will map out on the bit of coastline that you're looking at. And it finds the simplest uplift history that fits multiple tie points simultaneously. So the tie points need to have independent age control. Ideally, you don't only have two, but as it turned out, we did only have two. But that's the idea. And it's a bit complicated, and I'm happy to take questions on it either now or later. Later, probably best. Okay, so what we've got with our uplift modelling is, so these are the tie points. So at the top, we've got Boxgrove, which we assigned to the 485,000 year high stand. And then at the bottom, we've got Bembridge, which we've assigned to the 125,000 year high stand. And then you can see that Norton Farm maps out at pretty much the same elevation as Bembridge. We didn't actually use it as a tie point because we couldn't decide whether it was the 240,000 year high stand, which related to the OSL age, or the 200,000 year high stand, which related to the biostratigraphy. But we used it as a kind of test of our modelling, like, is it coming up in roughly the right place? So then you have this diagram in the bottom right-hand corner that is quite difficult to understand. It's basically a picture of this expected elevation, so where you would expect the different sea level high stands to hit the coast. And from this, you can see that the 125,000 year high stand, because it's bigger, even though there has been some uplift since the 240,000 year time high stand, they roughly sit at the same level. because the uplift is cancelled out by the fact that the second high stand is bigger than the first. And then you've also got this interesting thing where Boxgrove at 485,000 years is at pretty much the same elevation as the next high stand, which we don't seem to have a record of. So the simplest explanation involved two different uplift rates. So we had the slightly higher uplift rate until about 140,000 years ago, and then a much, much lower uplift rate since then. That was the only way we could get the that was basically the only way we could get the 125,000 year high stand in the right place. Otherwise it was up at about 17 meters, which it isn't. So there must have been this massive change in uplift rate, which we didn't really have any other evidence for anywhere else. So we started having to think about what that meant, which I'll go through in a couple of slides' time. So on to the conclusions. So we've got three new relative sea level values. And we tried doing it on the Pagham Formation beach deposits, but we didn't think they were reliable. And then that's just giving you the previous estimates. So you can see that our estimates are definitely lower than the previous estimates. They're not completely comparable because it's not entirely clear exactly whether they took the bottom of the sequence or the top of the sequence, and they weren't using wave cut platforms. But our estimates for the last interglacial seem to be a bit lower. Yeah, and the uplift is probably the most interesting part of the story. So the uplift rates are low, which we would expect. The uplift rates on the Cotentin Peninsula in France are also low from work that Jenny did there with a guy called Kevin Bedoya. And then you've got this big reduction in uplift rates. And so we were thinking to ourselves, well, what happened around about 140,000 years ago? And the answer is that there was a very large ice sheet on top of the Netherlands. And we have no idea what it was doing in the North Sea and over into the UK. So there is a line here on this map on the right-hand side, but I don't know if you can see the question marks that are all the way along that line. So it's possible that the reason we've got this massive change in uplift rate is actually that the underlying uplift rate is the same, but there was an ice sheet and it caused subsidence, and then it's uplifted afterwards, but it's offset the underlying uplift rate. Is that kind of making sense? Maybe everyone's looking a little bit. We can come back to it. So if that is the case, then it might help us with those little question marks on the edge of that ice limit. So, and that's just a little diagram in the middle of what ice sheets do to the land that cause it to go up and down. Okay, so the final set of thoughts is about preservation in the landscape, because it's a really interesting landscape because you've got these changes of bedrock. So I've already said that we're supposed to have had two high stand events at the same level in the highest part of the landscape, but there's no evidence for the second one. And so wondering whether, because we had such thick slope deposits, then that high stand wasn't cutting into bedrock, it was just cutting into the slope deposits, and so you wouldn't necessarily see it, or maybe it was reworked. The Aldingbourne Formation, which we didn't model, didn't use as a tie point, does seem to come in approximately at the high stand at 335,000 years ago. So that kind of helps because we have no idea how old that is. We don't have any reliable ages from that. You've got this overprinting of high stands again in the Brighton Norton Formation. And we're wondering whether the platform was cut in the 240,000 year high stand, but the sediments are older, potentially, younger, sorry. because the sea level came up to exactly the same place. And then finally, we've only got this one marine terrace preserved from the last high sea level event. And that seems likely to be because the bedrock is just that slightly bit stronger. And so it's more likely to be able to make a cliff formation. And that's the end of my thoughts. Oh, I've got some resources. Sorry. So various papers. I've created a virtual reality field trip if anyone wants to go to some of these places. And probably just worth highlighting about the Geological Conservation Review volume for Southern England, which is just about to come out in the Proceedings of the Geologists Association. 2 out of 5 of the papers are open access, just because they came in after Birkbeck signed an agreement that would make them open access. The others are not open access, so just email me if you want copies of them.